What makes things sticky? The secret forces between surfaces. Good evening, dear curious minds, and welcome to tonight's gentle exploration into one of the most wonderfully ordinary yet extraordinary phenomena that surrounds us every single day. I hope you're settling in comfortably wherever you happen to be watching from tonight. Perhaps you're nestled under soft blankets in your bedroom, the fabric fibers clinging to each other and to you through countless molecular interactions we'll soon discover together. Maybe you're curled up on a favorite couch as the day slowly gives way to evening's embrace, the upholstery holding its shape through adhesive forces between polymers that we rarely stop to consider. Or perhaps you're in some other cozy corner of the world, surrounded by objects that are all held together by the same invisible forces we're about to explore. I'm genuinely curious. Where in the world are you joining me from tonight? Are you watching from a bustling city where millions of adhesive connections hold skyscrapers together, or from a quiet countryside where the same molecular forces allow tree bark to cling to trunks and leaves to stay attached to branches? And what time is it where you are? Is the sun just beginning to set, painting the sky in those soft pastels that seem to whisper goodnight to the day, its light traveling to your eyes and sticking momentarily to your retinas through photochemical reactions that are themselves a form of molecular adhesion? Or perhaps darkness has already settled around you like a gentle, familiar friend, bringing with it the evening dew that will soon demonstrate the beautiful dance between water molecules and every surface they encounter? Tonight, we're going to take a wonderfully leisurely stroll through the invisible world of stickiness, that magical quality that allows a gecko to walk upside down on your ceiling with such casual confidence. That lets water droplets cling to your window after rain like tiny crystal ornaments. And that makes it possible for you to stick a note to your refrigerator with nothing more than a simple magnet. We'll discover together how the tiniest particles in our universe, particles so small that millions of them could dance on the head of a pin, conspire to create forces so subtle yet so powerful that they quite literally hold our world together, from the grandest mountains to the most delicate flower petals. We'll explore how these same forces that operate in the quantum realm of flickering electron clouds also manifest in ways you can observe right now around you, in the way your clothes drape against your body, in the condensation that might be forming on a cool glass nearby, in the very air you're breathing as gas molecules stick together just enough to behave as a fluid, rather than as isolated particles flying through space. Before we begin our journey into this sticky universe, I'd love to ask a small favor. If you find tonight's exploration soothing or illuminating, if it helps you see the ordinary world around you with new eyes of wonder, perhaps you might consider giving this video a gentle thumbs up, or even subscribing to join our growing community of nighttime learners. There's something quite magical about knowing that people all around the world, in different time zones and different seasons, are all sharing the same sense of wonder about how our universe works at its most fundamental level. Someone might be watching this as snow falls outside their window, each snowflake a masterpiece of molecular adhesion and crystalline architecture. Someone else might be listening as tropical rain patters against their roof, each droplet demonstrating the same hydrogen bonding principles we'll explore together tonight. I should probably offer a playful warning though. Sometimes these topics become so genuinely fascinating that you might find yourself more awake than when we started, your mind buzzing with new connections and insights about the adhesive world that surrounds you. If that happens, don't worry at all. Consider it a delightful side effect of curiosity. And know that the wonder we discover tonight will still be there tomorrow, ready to inspire your daytime thoughts and dreams. You might find yourself looking at a piece of tape with new appreciation, or watching water droplets on a window with the eyes of a scientist, or simply marveling at the fact that your morning coffee stays in your cup rather than spontaneously flying apart into individual molecules. So let's begin our gentle exploration into the secret forces that make things stick together, starting with a question that might seem almost childishly simple, but opens the door to mysteries that have puzzled humans for centuries and continue to drive cutting-edge research today. Why do things stick to other things at all? What prevents our universe from being nothing more than a chaotic swirl of isolated particles, each one bouncing off the others in eternal, meaningless collisions? Imagine, if you will, that you're holding a piece of tape in your hands right now, such an ordinary object, something you've probably used thousands of times without a second thought, yet when you press it against a surface and pull, it resists with a force that seems almost magical. What invisible hands are holding that tape in place? What secret conversations are happening between the tape and the surface at a level far too small for our eyes to see, in a realm where the normal rules of our everyday experience give way to the strange and beautiful laws of quantum mechanics and molecular physics? Tonight, we'll eavesdrop on those conversations and discover that the world of stickiness is really a story about some of the most fundamental forces that govern our entire universe. Forces that operate not just in laboratory experiments or exotic materials, but in every moment of your daily life, from the way your DNA molecules stick together in your cells, to the way stars hold onto their atmospheres across the vast emptiness of space. The story of stickiness is ultimately a love story, a tale of attraction that operates at every scale of existence, from the subatomic to the cosmic. It's about how matter reaches across the seemingly empty space between particles and says, in effect, "I want to be close to you." And, remarkably, this desire for closeness, this fundamental attractive force, is what allows complexity and beauty in life itself to exist in what would otherwise be a cold, empty universe of isolated particles. Let's take a gentle stroll through the invisible realm where atoms and molecules dance together in ways that create the sticky world we experience every day. Picture, for just a moment, that you could shrink yourself down smaller than the tiniest speck of dust, smaller than the smallest bacterium, smaller even than the wavelength of light itself, so small that individual atoms would loom before you like vast planetary systems. You'd find yourself in a world where the rules are different from anything we experience in our everyday lives, where particles don't just bump into each other and bounce away like billiard balls, but instead engage in subtle, almost romantic attractions that reach across the seemingly empty space between them, like invisible hands always reaching, always yearning for connection. At this unimaginably small scale, everything is in constant motion, not the steady, predictable motion of planets in their orbits, but a frenetic, jittery dance, driven by the fundamental energy that exists at the heart of all matter. Atoms vibrate and dance like leaves in a gentle breeze. Electrons swirl in clouds of probability around their nuclei like ethereal mists that exist in multiple places. Simultaneously, and even in what appears to be empty space, energy fluctuates like gentle waves on an invisible ocean that never quite settles into stillness. It's in this dancing, vibrating, fluctuating world, a world that exists in the space between the atoms that make up your own body at this very moment, that the first secrets of stickiness reveal themselves. And these secrets are more beautiful and more strange than anything our ancestors could have imagined when they first wondered why tree sap sticks to their fingers, or why water clings to the sides of a bowl. The most fundamental of these secrets bears the rather dignified name of van der Waals forces, named after Johannes van der Waals, a Dutch physicist who, in the late 1800s, began to understand that atoms and molecules aren't quite the hard, impenetrable spheres that earlier scientists had imagined them to be. Van der Waals was working in an era when the very existence of atoms was still being debated, when the idea that all matter was made of invisibly small particles was still a radical hypothesis rather than established fact. But through careful mathematical analysis of how gases behave under different temperatures and pressures, van der Waals realized that these tiny building blocks of matter have a kind of personal space around them, not empty space, but space filled with invisible influence, like the subtle gravitational field around a planet, but operating at the scale of atoms and extending for distances that are tiny even by atomic standards. These van der Waals forces are extraordinarily gentle, so gentle that if you tried to feel one directly, it would be like trying to feel the weight of a single grain of sand while wearing thick winter gloves, or like trying to hear a whisper from across a crowded stadium. Each individual van der Waals attraction is weaker than the chemical bonds that hold atoms together in molecules, weaker than the magnetic forces between permanent magnets, weaker even than the static electricity that makes your hair stand up when you rub a balloon against it. And yet, when billions upon billions of these tiny forces work together, and I mean truly astronomical numbers, more van der Waals interactions than there are stars in our galaxy, they become capable of supporting a gecko as it hangs upside down from your ceiling, completely defying what our everyday experience tells us should be possible. It's as if the universe has found a way to make weakness into strength through the simple expedient of having enough weak forces working together. To understand how such gentle forces can create such remarkable stickiness, let's imagine a dance, not a modern dance with just a few performers on a stage, but something like a vast medieval festival where thousands of couples are dancing simultaneously in an enormous ballroom. Picture each dancing pair as representing a single van der Waals interaction. One dancer is a molecule from one surface, the other is a molecule from a nearby surface, and they're dancing together across the narrow gap between those surfaces. Now, each individual couple is barely aware of the subtle attraction pulling them toward each other as they dance. The force between any two dancers is so gentle that they could easily break apart and find new partners if they wanted to. But multiply this by millions and millions of dancing pairs, all in the same ballroom, all feeling that same gentle pull toward each other, all moving in a coordinated rhythm that synchronizes their attractions. The collective effect becomes something much more substantial than any individual attraction, like the difference between trying to stop a single person from walking past you versus trying to stop an entire crowd, even if that crowd is moving very gently. This is precisely what happens when two surfaces come very, very close together. And by very close, I mean distances that are measured in nanometers, where a nanometer is so small that you could line up about 100,000 of them across the width of a human hair. At these tiny distances, countless molecular dancing pairs form across the gap between the surfaces, each one individually weak, but collectively creating what we experience as stickiness. But here's where the story becomes even more interesting, and where we begin to understand why preparation and technique matter so much in the art of making things stick. The strength of these attractions depends dramatically on distance, much more dramatically than our everyday experience would suggest. If you've ever played with two magnets, you've experienced something similar. When they're far apart, you feel nothing, but as you bring them closer together, the attraction suddenly becomes stronger, then stronger still, until that final moment when they snap together with surprising force. Van der Waals forces work similarly, but they're even more sensitive to distance. If two surfaces are separated by even a few molecular widths, distances so small that millions of them would fit across the width of a human hair, distances smaller than the wavelength of visible light, these attractive forces become vanishingly weak, so weak that thermal motion alone can overcome them. But bring those surfaces close enough that they're separated by just one or two molecular widths, and suddenly the forces become strong enough to hold things together with remarkable tenacity. This distance sensitivity is why preparation matters so much when you're trying to make things stick, and why technique can make the difference between a strong bond and a weak one. Think about applying a piece of tape to a surface. If you just lightly touch it to the surface and immediately try to pull it away, it might not stick very well at all, not because the tape is defective, but because you haven't given the molecules enough opportunity to get close together and form those millions of tiny van der Waals attractions. But if you press firmly, you're doing something quite remarkable at the molecular level. You're acting like a molecular matchmaker, pushing the two surfaces close enough together that billions of van der Waals attractions can form simultaneously. You're forcing the dancing pairs in our metaphor to come close enough to feel each other's presence and begin their synchronized dance of attraction. When you smooth out a piece of tape with your finger, running your fingertip along its length with steady pressure, you're essentially acting as a molecular ambassador, introducing countless molecules from the tape's adhesive to their potential partners on the surface you're sticking it to. Each smooth stroke brings more molecular pairs into that sweet spot of distance where attraction blooms, where the quantum mechanical forces that govern all matter can express themselves in ways that create macroscopic effects we can observe and use. There's something quite poetic about this, isn't there? The idea that stickiness is fundamentally about bringing things close enough together that they can feel each other's presence, close enough that the subtle attractive forces that exist between all matter, forces that are always there, always reaching out, but usually too weak to overcome the barriers that keep separate things separate, can finally express themselves and create connection. In a way, all stickiness is really about connection, about overcoming the barriers that normally keep separate things separate. And perhaps there's a metaphor here for human connections as well. How we need to come close enough to each other, through shared experiences and vulnerable moments, and patient presence, before the subtle forces of affinity and understanding can work their magic and create bonds that can withstand the various forces that might otherwise pull us apart. As we drift deeper into this molecular world, we encounter another character in our story of stickiness, one that might surprise you with its importance. This character is nothing less than the shape of space itself at the smallest scales, the topology and topography of surfaces that appear perfectly, smooth to our eyes and fingers, but reveal themselves to be vast landscapes of hills and valleys and caverns when viewed from a molecular perspective. Imagine running your hand across what feels like a perfectly smooth tabletop, perhaps the surface you're resting your arms on right now as you watch this. To your touch, it's flat and even, as smooth as glass. Your fingers detect no roughness, no bumps or scratches that would interfere with its apparent perfection. But if you could shrink down to molecular size and walk across that same surface, you'd find yourself embarking on a hiking adventure that would make the Rocky Mountains seem gentle by comparison. You'd encounter canyons deeper than the Grand Canyon, their walls rising steeply on either side of you as you tried to find a path forward. You'd climb peaks higher than Mount Everest, gasping in the thin atmosphere of molecular space as you scrambled over ridges and pinnacles that twist and turn in 3 dimensions like a mountaineer's fever dream. You'd discover crevices and caves extending deep into what seemed like solid matter, passages that wind and branch like underground river systems carved by eons of molecular erosion. This hidden topography, invisible to our eyes but very real to the molecules that must navigate it, plays a crucial role in how things stick together. When 2 surfaces come into contact, they don't just touch at their highest peaks like 2 mountain ranges pressed together. Instead, they also interlock, like 2 pieces of an incredibly complex 3-dimensional jigsaw puzzle, where every piece has been carved with fractal detail that extends down to the atomic level. Molecules from one surface settle into the valleys and crevices of the other, like water finding its way into every nook and cranny of a rocky landscape. Meanwhile, molecules from the second surface do the same in return, creating a mechanical interlocking that adds a whole new dimension to stickiness, one that works alongside the van der Waals forces we explored earlier, reinforcing and amplifying their effects. This mechanical interlocking explains why surface preparation is so important in adhesion, and why different preparation techniques can dramatically affect the strength of adhesive bonds. When you sand a piece of wood before gluing it, you might think you're just making it smooth, but from a molecular perspective, you're actually creating more surface area and more opportunities for this molecular interlocking to occur. You're increasing the number of nooks and crannies where molecules can settle and form connections, like creating more handholds on a climbing wall. But the story becomes even more intricate when we consider that surfaces aren't static landscapes frozen in time like photographs. At the molecular level, everything is in constant motion, not just the gentle swaying we might see in visible objects, but a frenetic dance driven by thermal energy, the kinetic energy that exists in all matter above absolute zero temperature. Atoms vibrate like tuning forks struck by invisible hammers. Molecules rotate and flex like microscopic gymnasts performing routines that never end. And the very surface itself undulates like a frozen wave that's not quite frozen, constantly shifting and reshaping itself at scales smaller than light wavelengths. This means that when 2 surfaces come together, they don't just interlock once and then remain static like 2 puzzle pieces snapped permanently into place. Instead, they engage in an ongoing molecular conversation, constantly adjusting and readjusting their connections as thermal motion continuously reshuffles the deck of molecular configurations. Think of it like 2 puzzle pieces that not only fit together, but continue to adjust their shape slightly to fit together even better over time, like dancers who start a dance as strangers but gradually learn each other's rhythms and preferences until they're moving together with perfect synchronization. This is why adhesive bonds often become stronger with time, why a piece of tape that might peel off easily if you try to remove it immediately after application becomes much more difficult to remove if you wait a few hours or days. During this time, something beautiful is happening at the molecular level that we might call the dance of accommodation. Molecules are finding their most comfortable positions relative to each other, like party guests who arrive at a social gathering and gradually form conversation groups based on shared interests and compatible personalities. The initial contact between surfaces might be somewhat awkward, with molecules not quite optimally positioned, some forced into higher energy configurations than they would prefer, like people at a party who haven't yet found their social rhythm. But given time measured in minutes or hours rather than the microseconds of molecular motion, the molecules settle into arrangements that maximize their attractive interactions and minimize any repulsive forces. They find the molecular equivalent of that perfect distance in a conversation where you can hear each other clearly without feeling crowded, where the chemistry of interaction flows naturally and effortlessly. This temporal aspect of stickiness reveals something profound about the nature of matter itself, something that challenges our everyday assumptions about the solid, unchanging nature of the objects around us. Nothing in our universe is truly static, despite appearances. Even what appears to be the most solid, unchanging surface, the table you might be leaning on, the walls of the room around you, the device you're watching this on, is actually a dynamic system in constant motion, constantly adapting, constantly seeking lower energy states and more stable configurations. It's like discovering that what you thought was a photograph is actually a slow-motion movie, where changes are happening constantly, but at a pace so different from our everyday experience that we don't normally notice them. The seemingly solid world around us is actually more like a very slow-flowing liquid, where molecules are constantly rearranging themselves in response to subtle changes in their environment. This dynamic view of matter helps explain why some adhesive bonds improve with age, while others deteriorate. If the molecular rearrangements lead to better fits and stronger attractions, the bond grows stronger over time. But if environmental factors like heat, moisture, or chemical contamination disrupt the optimal molecular arrangements, bonds can weaken or fail completely. Understanding this temporal dimension of adhesion has practical implications for everything from industrial manufacturing to everyday household repairs. It suggests that patience can be just as important as technique when creating strong adhesive bonds, that sometimes the best thing you can do after applying an adhesive is simply to wait, to give the molecules time to find their optimal arrangements and settle into configurations that will provide maximum strength and durability. Now let's take a gentle stroll through one of the most familiar yet extraordinary examples of stickiness in our daily lives. The stickiness of water itself. Water, that clear, seemingly simple substance that covers most of our planet and makes up most of our bodies, demonstrates principles of adhesion that are both beautiful and essential to life as we know it. Without water's unique adhesive properties, life on Earth as we understand it would be impossible. Have you ever watched a water droplet slowly making its way down a window after rain? Perhaps you can see such droplets right now if you look toward a window near you. There's something almost hypnotic about the way water moves down glass, not in a straight line like we might expect from simple gravity, but in a series of stops and starts, seeming to hesitate at certain points as if deciding which path to take, sometimes merging with other droplets to form larger ones, sometimes leaving behind tiny satellite droplets that cling to the glass with remarkable tenacity. What you're witnessing in this simple, everyday phenomenon is a complex dance between water molecules and the surface of the glass, mediated by forces we're now beginning to understand. Each droplet is held in its roughly spherical shape by the cohesive forces between water molecules, their preference for sticking to each other rather than spreading out into a thin film. But the droplet is also engaged in a constant negotiation with the glass surface, with some water molecules preferring to stick to the glass, while others prefer to stick to their fellow water molecules. Water molecules are particularly interesting from the perspective of stickiness, because they're what chemists call polar molecules. Imagine, if you will, that each water molecule is like a tiny magnet, but instead of having north and south poles, like the magnets you might stick to your refrigerator, water molecules have regions that are slightly positive and regions that are slightly negative. This polarity doesn't make them strongly charged like the ions in battery acid, but it does give them a subtle electrical personality that affects how they interact with other molecules. The reason for this polarity lies in the architecture of the water molecule itself. A water molecule consists of one oxygen atom bonded to two hydrogen atoms, but these atoms aren't arranged in a straight line. Instead, they form a bent shape, like a very shallow 5, with the oxygen atom at the vertex and the two hydrogen atoms forming the arms of the fifth. The oxygen atom is larger and more electronegative than the hydrogen atoms, which means it has a stronger pull on the electrons that form the chemical bonds. This creates a situation where the electrons spend more time near the oxygen atom than near the hydrogen atoms, giving the oxygen end of the molecule a slight negative charge and the hydrogen ends slight positive charges. When water molecules encounter each other, the slightly positive hydrogen atoms of one molecule are attracted to the slightly negative oxygen atoms of neighboring molecules. These attractions, called hydrogen bonds, are stronger than van der Waals forces, but still much weaker than the chemical bonds that hold the atoms together within each individual water molecule. You might think of hydrogen bonds as molecular handshakes, firmer than a casual nod of acknowledgement across a crowded room, but not as committed as a permanent embrace or a marriage bond. These hydrogen bonds are responsible for many of water's remarkable properties, properties that make it uniquely suited to its role as the medium of life. They're why water droplets form spherical beads on a waxed car surface rather than spreading out into thin films. The water molecules prefer to maintain their hydrogen bonds with each other, rather than forming weaker van der Waals interactions with the nonpolar wax. They're why water has such a high boiling point compared to other molecules of similar size. It takes extra energy to break the hydrogen bonds and separate the molecules enough for them to escape into the gas phase, and they're intimately involved in water's ability to stick to many different surfaces, creating the adhesive interactions that make so many biological and geological processes possible. But water's stickiness isn't just about water molecules sticking to each other. That would be cohesion. Water's stickiness also involves how water molecules interact with other substances, and this is where the story becomes particularly rich and complex. When water encounters a surface, several different things can happen, depending on the molecular nature of that surface. If the surface contains molecules that are also polar, molecules with their own regions of slight positive and negative charge, then the water molecules can form hydrogen bonds with the surface, just as they do with each other. This is what happens when water sticks to clean glass, or when it soaks into paper, or when it adheres to the inside of a plant's stem as it travels from roots to leaves in defiance of gravity. The glass in your windows, for example, contains silicon and oxygen atoms arranged in a network structure where the oxygen atoms have slight negative charges that can interact favorably with the positive hydrogen atoms in water molecules. This is why water spreads out on clean glass, rather than forming tight droplets. The water molecules are happy to break some of their hydrogen bonds with each other in order to form new hydrogen bonds with the glass surface. But if the surface is made of nonpolar molecules, molecules that don't have regions of positive and negative charge, then water can't form hydrogen bonds with it. In this case, the water molecules actually prefer to stick to each other rather than to the surface, forming those tight spherical droplets we see on waxed surfaces or on the feathers of a duck. The water molecules cluster together, minimizing their contact with the nonpolar surface and maintaining as many of their precious hydrogen bonds with each other as possible. This selective stickiness of water, its ability to distinguish between polar and nonpolar surfaces and respond accordingly, has profound implications for life on Earth. Consider how water moves through soil, carrying nutrients to plant roots. The soil is a complex mixture of mineral particles, many of which have polar surfaces that can form hydrogen bonds with water. This allows water to stick to soil particles, where it can be held against the pull of gravity long enough for plant roots to absorb it, along with the nutrients dissolved within it. If water couldn't stick to soil particles, if soil were made entirely of nonpolar materials like wax, then water would simply run through it like water through a sieve, and plants would have no way to obtain the water they need for survival. The adhesive properties of water are literally what make terrestrial plant life possible. Or think about how water moves up through the narrow tubes in plant stems, defying gravity to reach leaves that might be hundreds of feet above the ground in the tallest trees. This remarkable phenomenon, called transpiration, depends entirely on the adhesive properties of water, and represents one of the most beautiful demonstrations of molecular stickiness in action. Inside the narrow tubes of a plant's vascular system, tubes that are often only a few dozen micrometers in diameter, narrower than a human hair, water molecules form hydrogen bonds with the polar molecules that line the tube walls. These might be cellulose molecules in the cell walls or specialized proteins that help transport water, but the water molecules also maintain their hydrogen bonds with each other, creating an unbroken chain of molecular handshakes that extends from the roots all the way to the leaves. When water evaporates from the surface of a leaf through the microscopic pores called stomata, it's like someone at the end of a very long human chain letting go of the hand they were holding. The entire chain feels the tension and responds by moving forward slightly to maintain the connection. In the case of water in plants, this creates a gentle but persistent pulling force that can draw water up through the entire plant, sometimes for distances of more than 300 feet in the tallest redwood trees. The fact that this works at all is a testament to the remarkable strength of collective molecular attractions. Each individual hydrogen bond is quite weak. You could break one with the energy contained in the gentlest tap of your finger, less energy than it takes to flip a light switch or blink your eye. But when millions and millions of these bonds work together, like threads in a rope or fibers in a cable, they become capable of moving. Tons of water against the pull of Earth's gravity, day after day, year after year, for the entire lifetime of the tree. This principle, that many weak attractions working together can create strong effects, is fundamental to understanding stickiness in all its forms. It appears again and again in nature, from the way geckos walk on ceilings to the way our own cells stick together to form tissues and organs. It's a principle that applies not just to molecules, but to ecosystems, communities, social movements, and many other complex systems in our world. There's something almost philosophical about this aspect of molecular behavior. It suggests that strength and permanence don't always require individual components to be strong or permanent themselves. Instead, they can emerge from the collective action of many gentle, temporary connections, like a murmuration of starlings, where individual birds follow simple rules but create complex, beautiful patterns through their collective behavior. This principle applies to human communities as well. Strong societies aren't necessarily built from strong individuals who never need help, but often from networks of people who support each other through countless small acts of kindness and cooperation. Like hydrogen bonds in water, each individual connection might be modest, but the collective effect can be remarkably resilient and powerful. The story of water's adhesive properties also illustrates the importance of molecular recognition, the ability of molecules to distinguish between different types of surfaces and respond appropriately. Water doesn't just stick to everything equally, it makes choices based on the molecular characteristics of what it encounters. This selectivity is crucial for many biological processes. Cell membranes, for example, are constructed from molecules that have both polar and nonpolar regions. The polar regions interact favorably with water, while the nonpolar regions avoid water and cluster together. This creates the lipid bilayer structure that forms the boundary of every living cell, a boundary that is permeable to some substances but not others, allowing cells to maintain their internal environment while still exchanging materials with their surroundings. As we continue our gentle exploration, let's turn our attention to one of nature's most famous demonstrations of molecular stickiness: the extraordinary ability of geckos to walk on walls and ceilings with apparent ease, defying gravity in ways that have captured human imagination for millennia. This remarkable feat has puzzled naturalists for centuries and has only recently been understood well enough to inspire new technologies that might one day allow humans to climb walls like the superheroes we see in movies. For the longest time, people assumed that geckos must have some kind of sticky secretion on their feet, like tiny biological glue dispensers that they could turn on and off at will. Early naturalists proposed that gecko feet might work like suction cups, creating areas of low pressure that would hold them to surfaces through the difference in atmospheric pressure. Others thought perhaps their feet were covered in tiny hooks that could grab onto microscopic irregularities in surfaces, like miniature versions of the hook and loop fasteners we know as Velcro. But when scientists finally developed instruments sensitive enough to study gecko feet at the molecular level, electron microscopes that could reveal details smaller than the wavelength of light and force, measuring devices that could detect attractions weaker than the weight of a single cell, they discovered something far more elegant and surprising than any of these earlier hypotheses had suggested. Gecko feet, it turns out, are covered in millions upon millions of incredibly tiny hairs called setae. Each of these setae is far too small to see with the naked eye, about 10 times thinner than a human hair, and only about as long as the diameter of a human hair. If you could somehow gather up all the setae from a single gecko's foot, they would be virtually invisible to the naked eye, like the finest imaginable brush made from strands of spider silk. But that's just the beginning of the story, because the architecture of gecko feet operates at multiple scales of size, like a fractal structure that reveals new levels of detail the more closely you examine it. Each of these tiny setae branches into even smaller structures called spatulae, and here we need to pause for a moment to appreciate just how small these spatulae really are. The spatulae at the tips of gecko setae are so small that they approach the realm where individual molecules become significant. Each spatula is only about 200 nanometers wide, and to put that in perspective, you could line up about 500 spatulae across the width of a single human hair. They're smaller than the wavelength of visible light, which means that even if you had the most powerful optical microscope ever built, you couldn't see individual spatulae clearly because the light waves themselves are too large to resolve such tiny details. When a gecko places its foot on a surface, these millions of tiny spatulae come into extraordinarily close contact with the molecular landscape of that surface. Remember our earlier discussion of van der Waals forces, those gentle attractions that exist between all molecules when they're close enough together? Gecko feet are essentially biological machines that have been optimized by millions of years of evolution for maximizing the number of van der Waals interactions between the gecko and whatever surface it's walking on. The genius of this system lies not in any single strong adhesive force, but in the sheer number of weak adhesive interactions working simultaneously. A single gecko foot might have as many as 2 billion spatulae in contact with a surface at any given moment. Even though each individual van der Waals interaction is extraordinarily weak, when you multiply that weakness by 2 billion, the result is strong enough to support the gecko's entire body weight, even when it's hanging upside down from a smooth ceiling. To put this in perspective, imagine trying to lift a heavy object using rubber bands. A single rubber band might be able to lift only a few ounces, but if you could somehow attach thousands of rubber bands to the same object, their combined strength could lift hundreds of pounds. The gecko's adhesive system works on a similar principle, except instead of thousands of rubber bands, it uses billions of molecular interactions, each one weaker than any rubber band, but collectively creating remarkable adhesive strength. But here's the truly remarkable part of the gecko story. Geckos can turn this adhesion on and off almost instantaneously. They don't get permanently stuck to surfaces like an insect caught on flypaper, and they don't leave any residue behind when they walk. They can run across a ceiling at full speed, making and breaking adhesive contact with each step in a fraction of a second. How do they manage this seemingly impossible feat? The secret lies in the geometry of their foot hairs and the way geckos control the angle at which these hairs contact the surface. When the spatulae are pressed against a surface at just the right angle, roughly parallel to the surface, maximum contact is achieved and adhesion is strong. The spatulae conform to the microscopic topography of the surface like molecular scale molding putty, filling in tiny valleys and wrapping around microscopic hills to maximize the number of van der Waals interactions. But when the gecko changes the angle slightly, something it can do by subtle adjustments of its foot position and the way it flexes its toes, the contact area decreases dramatically and the adhesion weakens enough for the gecko to lift its foot. It's rather like the difference between pressing the flat side of a piece of tape against a surface versus trying to stick the tape using just its edge. The same adhesive material behaves very differently depending on how much surface area is actually in contact. This angular dependence of gecko adhesion is so precise that changing the angle by just a few degrees can make the difference between strong adhesion and easy release. It's like having an adhesive system with a built-in on-off switch that can be controlled through purely mechanical means, without any need for chemical changes or energy input. The discovery of gecko adhesion mechanisms has inspired engineers to develop gecko-inspired adhesives that work on the same principles. These biomimetic materials use arrays of tiny synthetic hairs, usually made from polymers like silicone, to create strong, reversible adhesion without any chemical glue. Some of these materials can support remarkable weights. Imagine being able to hang a full-grown adult from the ceiling using nothing more than a small patch of gecko-inspired tape. Creating artificial gecko tape isn't as simple as just making tiny hairs, though. The hairs need to be exactly the right size and shape, they need to be made from materials with the right mechanical properties, and they need to be arranged in precise patterns that allow them to work together effectively. It's like trying to recreate a Swiss watch by examining it under a magnifying glass. You can see the general principles, but capturing all the subtle details that make it work requires extraordinary precision and craftsmanship. But the implications of gecko-inspired adhesion go far beyond just creating new types of tape. Researchers are exploring these principles for everything from medical bandages that stick firmly but remove painlessly. Imagine bandages that could hold strongly enough to stay in place during surgery but release cleanly without damaging delicate skin, to climbing equipment for astronauts working in the zero-gravity environment of space stations, to tiny robots that could walk on walls and ceilings for inspection and repair tasks in places too dangerous for humans to go. Some researchers are even investigating whether gecko-inspired adhesion could be used for temporary architectural structures, buildings that could be assembled without permanent fasteners, and then disassembled and moved to new locations without leaving any trace behind. It's a vision of reversible construction that could revolutionize how we think about building and living spaces. There's something wonderful about the fact that geckos solved this engineering challenge millions of years before humans even knew it was a challenge to be solved. Evolution, through countless generations of trial and improvement, arrived at a solution that our most sophisticated engineers are only now beginning to understand and replicate. It's a humbling reminder that nature is full of such elegant solutions to complex problems, solutions that have been tested and refined over timescales that dwarf human history. This reminds us that the natural world around us is essentially a vast library of time-tested technologies, each one refined over millions of years of evolutionary experimentation. When we study how things stick together in nature, we're not just satisfying our curiosity, we're also discovering principles that might help us solve human challenges in ways that are more efficient, more sustainable, and more elegant than anything we might invent from scratch. The gecko's approach to stickiness also illustrates another important principle, that the best solutions are often reversible ones. In nature, being able to unstick is just as important as being able to stick. A gecko that could stick to surfaces but couldn't unstick would quickly find itself in serious trouble, unable to flee from predators or pursue prey, or simply move around to find food and mates. This principle of reversible adhesion appears throughout the natural world in fascinating variations. Tree frogs use similar strategies to navigate wet, slippery surfaces, combining molecular adhesion with mechanical gripping and surface tension effects to maintain their hold on leaves and branches. Spiders can walk on their own webs without getting trapped by the same sticky silk that ensnares their prey, using specialized foot structures and behavioral techniques that allow them to selectively interact with sticky and non-sticky strands of their webs. Even at the cellular level, our bodies are constantly forming and breaking molecular connections that allow cells to adhere to each other when they need to, but also to separate when growth, healing, or movement requires it. White blood cells, for example, can stick to blood vessel walls when they need to exit the circulatory system to fight infections, but they can also release and move through tissues when their job is done. The study of reversible adhesion is leading to new understanding of how biological systems maintain the delicate balance between stability and flexibility that life requires. Too much adhesion in organisms becomes stuck in place, unable to adapt to changing conditions. Too little adhesion and structures fall apart, unable to maintain the organization that makes life possible. As we delve deeper into our exploration of stickiness, let's take a gentle stroll through the fascinating history of how humans have learned to create and control adhesion for their own purposes. This is a story that spans thousands of years and reveals how our understanding of stickiness has evolved from purely practical trial and error to sophisticated molecular engineering. It's also a story about human ingenuity and our species' remarkable ability to observe natural phenomena and gradually learn to replicate and improve upon them. The earliest human adhesives were discovered rather than invented, found in the natural world by our ancestors who were keen observers of their environment. Archaeological evidence suggests that our ancestors were using natural sticky substances at least 200,000 years ago, long before the development of agriculture, writing, or most of the technologies we consider fundamental to human civilization. These early adhesive pioneers discovered that certain trees, when cut or damaged, would bleed resins and saps that could be collected and used to stick things together. They learned that birch bark, when heated in the absence of air, would produce a tar-like substance that remained sticky when cool and could be used to attach stone tools to wooden handles. They discovered that the bones, hooves, and hides of animals, when boiled for hours, would yield glues that dried hard and strong. Picture these early experimenters working around their fires in the evening, perhaps after a successful hunt, carefully observing how different materials behaved when heated, cooled, mixed, or aged. They had no understanding of molecules or chemical bonds, but through patient trial and error, they learned to identify and utilize the sticky properties of various natural substances. They were conducting sophisticated materials science experiments, testing how different substances behaved under different conditions, learning to modify natural materials to enhance their adhesive properties. They discovered that some tree saps become stickier when heated, allowing them to be applied more easily and then setting to a harder, more durable consistency as they cooled. They learned that certain animal-based glues became stronger when they were allowed to dry slowly rather than quickly, and that the addition of certain plant materials could improve the flexibility or water resistance of their adhesives. In many ways, these ancient craftspeople were the first adhesive engineers. Even though they had no molecular theory to guide their work, they developed standardized recipes and techniques that could be passed down from generation to generation, creating the first technology transfer programs in human history. A successful hunter might teach others in the tribe how to prepare the perfect pine pitch for hafting spear points, or how to mix bone glue with plant fibers to create composite materials with properties superior to either component alone. One of the most ingenious early adhesive applications was the development of laminated materials, essentially the world's first composite technologies. Ancient bowmakers learned to glue together different types of wood, horn, and sinew to create bows that were far more powerful and efficient than anything that could be made from a single material. These composite bows represented an early understanding that adhesives could be used not just to attach separate pieces, but to create entirely new materials with properties that exceeded those of their individual components. The principle behind these ancient composites is the same one that governs modern materials like fiberglass, carbon fiber, and even reinforced concrete. Different materials are combined using adhesive bonds to create a composite structure where each component contributes its best properties to the whole, while the adhesive holds everything together and allows the different materials to work in harmony. In a composite bow, the wood provides flexibility and lightness, the horn provides strength and compression when the bow is drawn, the sinew provides strength and tension on the back of the bow, and the adhesive holds it all together while distributing stresses evenly throughout the structure. The result is a bow that can store and release far more energy than a simple wooden bow of the same size, giving arrows greater speed and range. As civilizations developed and became more complex, so did adhesive technologies. The Egyptians became masters of adhesive arts, developing sophisticated glues for everything from furniture making to boat building to the complex process of mummification. They learned to create adhesives that could withstand the test of time. Some Egyptian artifacts still hold together after thousands of years, a testament to both the quality of their adhesives and their deep understanding of how to prepare surfaces for optimal bonding. Egyptian furniture makers developed techniques for creating seamless joints between pieces of wood using animal-based glues combined with mechanical interlocking joints. They understood that the strongest connections often combined multiple adhesion mechanisms: chemical bonding through the glue, mechanical interlocking through carefully shaped joints, and sometimes even additional reinforcement through pegs or wrappings. The process of mummification required adhesives that could preserve organic materials for millennia, while also binding together the complex layers of wrappings that protected the body. Egyptian embalmers developed resins and gums that not only acted as preservatives, but also created strong adhesive bonds between layers of linen wrappings, essentially creating a composite material that was both protective and durable. The Romans advanced adhesive technology even further, developing hydraulic cements that could set underwater and creating massive concrete structures that relied on adhesive chemistry to bind together aggregate materials. Roman concrete was a marvel of ancient engineering, made from a mixture of volcanic ash, lime, and water that underwent chemical reactions to create a stone-like material that actually grew stronger with age and could withstand the stresses of massive architectural projects like the Pantheon and the aqueducts. The Romans didn't understand the molecular mechanisms of cement chemistry, but they empirically discovered principles of adhesion that we now know are based on complex chemical reactions that create strong crystalline bonds between particles. Their concrete was so advanced that some Roman structures have survived in excellent condition for over 2,000 years, while some modern concrete structures begin to deteriorate after just a few decades. For centuries after the fall of Rome, adhesive technology advanced slowly, primarily through craft knowledge passed down from master to apprentice within specialized guilds. Each trade developed its own specialized adhesives and techniques. Bookbinders had their carefully guarded recipes for flexible glues that wouldn't crack when pages were turned. Shipbuilders had their secret formulations for caulking compounds that could seal the gaps between planks while remaining flexible enough to accommodate the movement of wooden hulls in heavy seas. Artists had their complex recipes for media and varnishes that would protect their paintings for centuries. This craft-based approach to adhesive technology meant that knowledge was often localized and closely guarded. A master craftsperson might spend decades perfecting a particular adhesive formulation, but that knowledge might die with them if they failed to pass it on to a worthy apprentice. Progress was slow and often lost to wars, plagues, or social upheavals that disrupted the careful chains of knowledge transmission. The Industrial Revolution of the 18th and 19th centuries brought new pressures and new opportunities to adhesive technology. Suddenly, there was a need for adhesives that could work with new materials like metals and early synthetic substances that could withstand the stresses and temperatures of mechanized production, and that could be manufactured in large quantities with consistent properties from batch to batch. This drove the development of the first synthetic adhesives in the late 19th and early 20th centuries. Chemists began to understand that adhesion was fundamentally about molecular interactions, and they started designing molecules specifically to create desired adhesive properties, rather than simply modifying natural materials through trial and error. The invention of synthetic polymers, long-chain molecules created through controlled chemical reactions, opened up entirely new possibilities for adhesive design. Instead of being limited to natural substances that happened to be sticky, chemists could now design molecules from scratch to have precisely the adhesive characteristics needed for specific applications. They could create adhesives that remained flexible at low temperatures for Arctic applications, or that cured quickly under heat for high-speed manufacturing processes, or that bonded strongly to specific types of surfaces while remaining easy to remove from others. This molecular design approach led to the development of pressure-sensitive adhesives, the technology behind modern tape. These remarkable materials remain tacky at room temperature, allowing them to form bonds simply through contact pressure, but they can be removed without leaving residue under normal conditions. The chemistry behind pressure-sensitive adhesives involves carefully balancing molecular weight, cross-linking density, and tackifying agents to create just the right degree of stickiness, strong enough to hold reliably, but not so strong as to damage surfaces during removal. Creating a good pressure-sensitive adhesive is like tuning a musical instrument. Every component must be precisely adjusted to work in harmony with every other component. The base polymer provides the fundamental adhesive properties. Cross-linking agents control how the molecules connect to each other. Tackifying resins adjust the surface stickiness, and various additives fine-tune properties like temperature resistance, aging stability, and compatibility with different surface types. The space program of the mid-20th century pushed adhesive technology even further, requiring adhesives that could function in the extreme conditions of space: perfect vacuum, intense radiation, and temperature swings from hundreds of degrees below zero to hundreds of degrees above zero, sometimes occurring within minutes as spacecraft moved between sunlight and shadow. These challenges led to the development of structural adhesives so strong that they could actually replace mechanical fasteners like bolts and rivets in some applications. Imagine glue strong enough to hold together the hull of a spacecraft, reliable enough to trust with the lives of astronauts, and stable enough to maintain their properties for years in the harsh environment of space. The development of space-grade adhesives required new understanding of how molecular structures behave under extreme conditions. Chemists had to design polymer molecules that wouldn't become brittle in the extreme cold of space or degrade under the intense ultraviolet radiation from the unfiltered sun. They had to create formulations that would cure properly in vacuum, where traditional solvents couldn't evaporate in the normal way. Today, we're entering what might be called the golden age of adhesive technology. Computer modeling allows chemists to design molecules with predicted properties before they even synthesize them, dramatically speeding up the development of new adhesive materials. Scientists can now use sophisticated software to simulate how different molecular structures will behave under various conditions, predicting their adhesive strength, flexibility, temperature resistance, and other properties with remarkable accuracy. Nanotechnology enables the creation of adhesives that work at the scale of individual molecules, with precision that would have been unimaginable just a few decades ago. Researchers can now engineer surfaces with molecular-scale features that control exactly how adhesives interact with them, creating bonds with precisely tailored properties. Biomimetics, the practice of taking inspiration from natural adhesion systems, has opened up entirely new approaches to stickiness. Scientists studying everything from gecko feet to muscle glue to spider silk are discovering principles that lead to adhesives with capabilities that didn't exist before. Some of these bio-inspired adhesives can switch between sticky and non-sticky states in response to changes in pH, temperature, or electrical signals, creating smart adhesives that can adapt their properties to changing conditions. We now have biocompatible adhesives that can be safely used inside the human body for medical applications. Biodegradable adhesives made from renewable resources that break down harmlessly in the environment, and ultra-strong adhesives that can bond materials that were previously considered impossible to glue together, like certain plastics, glasses, and ceramics. Some of the most exciting developments involve adhesives that can heal themselves when damaged, much like biological tissues. These self-healing adhesives contain microcapsules filled with healing agents that are released when the adhesive is cracked or damaged, automatically repairing the bond and restoring its strength. Yet for all of our technological sophistication, the fundamental principles remain the same ones that our ancestors discovered through patient experimentation thousands of years ago. Stickiness is still about bringing surfaces close enough together that molecular attractions can operate effectively. It's still about matching the properties of the adhesive to the properties of the surfaces being bonded. And it's still about understanding that the strongest bonds often come not from a single powerful force, but from many smaller forces working together in harmony. There's something beautifully human about this continuity across time. The idea that a modern aerospace engineer designing adhesives for spacecraft and an ancient craftsperson attaching a stone point to an arrow shaft are both engaged in fundamentally the same endeavor, understanding and harnessing the molecular forces that hold matter together to create tools and structures that serve human needs. This continuity reminds us that technology isn't just about creating new things, but about deepening our understanding of timeless principles and finding ever more sophisticated ways to apply them. The same curiosity that drove our ancestors to experiment with tree saps and animal glues continues to drive modern researchers as they explore the frontiers of molecular engineering and biomimetic design. Now let's take a gentle stroll through the fascinating distinction between chemical bonds and physical adhesion. Two different approaches to stickiness that operate according to different rules and create different types of connections. Understanding this distinction helps us appreciate why some things stick together temporarily while others form permanent bonds, and why the same adhesive might behave very differently under different conditions or with different surface preparations. Physical adhesion, which we've been exploring primarily so far, is like a very enthusiastic handshake between molecules. The molecules remain essentially unchanged by the interaction. They're still the same molecules they were before they met, with the same chemical identity and the same internal structure. But they're now attracted to each other through various intermolecular forces that reach across the space between them like invisible hands. Van der Waals forces, hydrogen bonds, and electrostatic attractions all fall into this category of physical adhesion. These forces operate through the external electromagnetic fields that surround molecules, creating attractions and repulsions based on the spatial arrangement of electric charges within and around the molecules. These physical interactions are typically reversible, like social connections that can be formed and dissolved without permanently changing the people involved. Just as you can shake hands with someone and then let go without either of you being fundamentally altered by the experience, molecules that are connected through physical adhesion can be separated without fundamentally changing their chemical nature. This is why you can peel tape off a surface, or why water droplets can evaporate from a window, or why a gecko can lift its foot from a wall. The energy required to break physical adhesive bonds is generally much less than the energy that would be needed to break the chemical bonds within the molecules themselves. It's like the difference between convincing someone to let go of your hand versus convincing them to give you one of their fingers. One requires gentle persuasion, the other would require drastic intervention. Chemical adhesion, on the other hand, is more like molecular marriage or adoption. In chemical bonding, molecules actually share electrons or exchange them completely, creating new chemical entities that are fundamentally different from the original molecules. When chemical bonds form between an adhesive and a surface, atoms from the adhesive literally become chemically bonded to atoms in the surface, creating a connection that can't be undone without breaking those chemical bonds, and fundamentally changing the chemical nature of the materials involved. To understand this distinction more clearly, imagine the difference between holding hands with someone and having your hands surgically connected. In both cases, your hands are joined together, but the nature of the connection and the ease of separation are dramatically different. Physical adhesion is like holding hands, intimate and strong, but reversible without permanent change. Chemical adhesion is like surgical connection, even stronger, but requiring significant intervention to undo and likely to leave permanent changes even after separation. Many of the strongest adhesives we use in industry and construction work through chemical bonding. Epoxy adhesives, for example, consist of two components that, when mixed together, undergo chemical reactions that create a three-dimensional network of chemical bonds. This network physically entangles the molecules of the surfaces being bonded, creating connections that can be stronger than the materials themselves. When an epoxy bond cures, what's happening at the molecular level is quite remarkable. The molecules in the adhesive are literally reaching out and forming chemical bonds, with compatible molecules on the surfaces being joined. If those surfaces have been properly prepared, cleaned to remove contaminants, and perhaps chemically treated to provide reactive sites, the resulting bonds can be so strong that attempting to separate the bonded materials will cause them to break at some other location rather than at the adhesive interface. This is why surface preparation is so crucial for chemical adhesives. Physical adhesion can work even on contaminated surfaces, though not optimally. The van der Waals forces and other physical interactions can still operate even in the presence of dirt, oils, or other contaminants, though their effectiveness may be reduced. But chemical adhesion often requires surfaces that are not just clean, but chemically compatible with the adhesive system being used. Sometimes this means applying primer coatings that provide chemical groups that the adhesive can bond to. A primer is essentially a molecular translator, providing chemical functionality that can react with both the surface and the adhesive, creating a bridge between materials that might not otherwise be chemically compatible. The time factor behaves differently in chemical versus physical adhesion as well. Physical adhesion usually happens almost instantaneously. As soon as molecules get close enough together, the attractive forces begin to operate at the speed of electromagnetic interactions, which is essentially instantaneous on human timescales. You can see this when you touch a piece of tape to a surface. The adhesion is immediate. But chemical adhesion often requires time for the chemical reactions to occur. This is why many strong adhesives have what are called working times and cure times, periods during which the chemical reactions are progressing but not yet complete. During the working time, the adhesive remains malleable and can be repositioned or adjusted. During the cure time, chemical reactions are proceeding to create the final bond strength. The rate of these chemical reactions depends on many factors, including temperature, humidity, the presence of catalysts, and the specific chemistry of the adhesive system. Some chemical adhesives can be formulated to cure very quickly, in seconds or minutes, for applications where speed is important. Others are designed to cure slowly, over hours or even days, for applications where extended working time is needed or where the stresses of rapid curing might damage delicate assemblies. Temperature affects these two types of adhesion differently as well. Physical adhesion generally becomes weaker as temperature increases, because higher temperatures mean more molecular motion, which can overcome the relatively weak intermolecular forces. This is why tape becomes less sticky on a hot day, or why ice cubes start to slide around in a glass as they warm up. But chemical adhesion often becomes stronger with moderate heating, because higher temperatures provide the energy needed for chemical reactions to proceed more quickly and completely. Many chemical adhesives are actually designed to be cured at elevated temperatures to achieve maximum bond strength. However, excessive heat can also cause chemical bonds to break down, so there's usually an optimal temperature range for any given adhesive system. Some of the most sophisticated modern adhesives combine both physical and chemical adhesion mechanisms in clever ways. They might start with physical adhesion that provides immediate bond strength, allowing parts to be handled and positioned quickly. Then, over time, chemical reactions proceed to develop additional chemical bonds that provide ultimate strength and durability. This dual-mode approach gives these adhesives the advantage of immediate handling strength combined with long-term reliability. It's like a relationship that starts with immediate physical attraction but develops deeper emotional bonds over time. Both components contribute to the overall strength and stability of the connection. Understanding the difference between chemical and physical adhesion also helps explain why some adhesive failures happen and how they can be prevented. If an adhesive bond is designed to work through chemical adhesion, but the surface preparation doesn't allow chemical bonds to form properly, the connection might rely only on much weaker physical adhesion. The bond might seem fine initially, but fail unexpectedly under stress or environmental conditions that would be easily handled by proper chemical bonds. Conversely, if a connection is designed to be temporary and reversible, relying primarily on physical adhesion, but chemical reactions occur. Over time, due to heat, UV exposure, or other environmental factors, what was supposed to be removable might become permanent. This is why some tapes become much harder to remove if left in place for long periods, especially in hot, sunny environments where chemical reactions are more likely to occur between the adhesive and the surface. The biological world makes extensive use of both types of adhesion, often in ingenious combinations that demonstrate principles we're still learning to apply in our own technologies. Our own bodies use chemical cross-linking to create permanent structures like bones and teeth, where calcium phosphate crystals are bonded together through chemical interactions to create materials that can last a lifetime while still being capable of repair and remodeling. But biological systems also rely extensively on physical adhesion for many cellular functions that need to be reversible and adjustable. Cell membranes, for example, are held together primarily through physical interactions between lipid molecules, interactions that are strong enough to maintain the integrity of cellular boundaries, but flexible enough to allow membranes to fuse and separate as needed for cellular processes like division, secretion, and membrane repair. Blood clotting provides a beautiful example of how both mechanisms can work together in a coordinated biological process. Initially, platelets aggregate at the site of injury through physical adhesion, forming a temporary plug that can slow bleeding within seconds. But then chemical reactions begin to occur, creating fibrin threads that chemically cross-link to form a more permanent clot structure. The final clot owes its strength to both the physical entanglement of cells and fibers and the chemical bonds that hold the fibrin network together. Even in something as simple as the way our skin cells stick together, we find both chemical and physical adhesion working in harmony. Cells are connected by protein structures called desmosomes and tight junctions that involve both chemical bonds within the proteins themselves and physical interactions between different cellular components. This combination creates connections that are strong enough to hold our skin together under normal stresses, but can also be remodeled as needed for growth, healing, and normal cellular turnover. This interplay between chemical and physical adhesion appears throughout nature and technology, and it's part of what makes the study of stickiness so rich and complex. We're not just dealing with a single phenomenon, but with a whole family of related mechanisms that can work independently or in combination to create the sticky world we experience. As our understanding of these mechanisms has grown more sophisticated, we've been able to design adhesive systems that take advantage of both approaches in precisely controlled ways. Smart adhesives might use physical adhesion for positioning and initial bonding, then trigger chemical reactions through heat, light, or chemical exposure to create permanent attachment. Removable adhesives might be designed to rely primarily on physical interactions, with chemical structures chosen specifically to avoid unwanted chemical bonding with common surface materials. The future of adhesive technology likely lies in this kind of molecular-level engineering, where we design adhesive systems with full understanding of how chemical and physical interactions will behave under different conditions. It's a level of control and precision that would have seemed magical to early adhesive craftspeople, yet it's built on the same fundamental principles they discovered through careful observation and experimentation. Let's take a gentle stroll now into one of the most mysterious and fascinating aspects of stickiness: the quantum mechanical forces that operate at the very smallest scales of matter. This might sound intimidatingly technical at first, but the quantum world reveals some of the most beautiful and surprising secrets about why things stick together at all, secrets that connect the everyday experience of stickiness to the deepest laws that govern our universe. When we've talked about van der Waals forces throughout our exploration tonight, we've described them as gentle attractions between molecules, but we haven't really explored where these forces come from in the first place. The answer lies in the strange and wonderful realm of quantum mechanics, where particles can exist in multiple states simultaneously, where the very act of observation changes the reality being observed, and where empty space itself is full of energy and activity. To understand quantum stickiness, we need to imagine electrons not as tiny planets orbiting atomic nuclei in predictable paths, but as clouds of probability that surround the nucleus in complex three-dimensional patterns. These electron clouds aren't static structures frozen in place like architectural drawings. Instead, they're constantly shifting and fluctuating, creating regions of slightly higher and lower electron density that change from moment to moment in ways that are fundamentally unpredictable yet follow statistical patterns. Picture, if you will, a gentle storm cloud that's constantly changing shape, with areas of density moving around within it like currents in water or wind patterns in the atmosphere. Sometimes one side of the cloud becomes a bit denser than the other, creating a temporary imbalance that exists for only fractions of a second before the cloud shifts and the imbalance moves somewhere else or disappears entirely. This is essentially what happens with electron clouds around atoms and molecules, but at timescales that are measured in femtoseconds, quadrillionths of a second, timescales so short that light itself can travel only a few hundred nanometers during such intervals. When an electron cloud temporarily becomes denser on one side of an atom, that side becomes slightly more negative while the opposite side becomes slightly more positive. This creates what scientists call an instantaneous dipole, a temporary separation of charge that appears and disappears in tiny fractions of a second, like lightning that flickers too quickly for the eye to follow. Now here's where the quantum story becomes really interesting, and where we begin to see how the microscopic world of quantum mechanics connects to the macroscopic world of everyday stickiness. These instantaneous dipoles don't just exist in isolation, like random flickers of light in an empty room. Instead, when one atom develops a temporary dipole, it influences the electron clouds of nearby atoms through electromagnetic interactions, encouraging them to develop complementary dipoles that enhance the overall attractive interaction. It's like a quantum version of the wave that spreads through a crowd at a stadium. One person's movement influences their neighbors, which influences their neighbors' neighbors, and so on, creating a coordinated wave of motion that spreads outward from the initial disturbance. In the case of atomic dipoles, one atom's temporary charge separation induces complementary charge separations in nearby atoms, creating a synchronized fluctuation that enhances the attractive forces between them. These synchronized fluctuations in electron density create what are called London dispersion forces, named after Fritz London, the physicist who first explained their quantum mechanical origin in the 1930s. London dispersion forces are one of the main components of van der Waals attractions, and they represent something quite remarkable: attractive forces that arise from pure quantum mechanical uncertainty, from the fundamental fact that electrons can't have perfectly defined positions and are always fluctuating around their average locations according to the principles of quantum mechanics. In essence, quantum mechanics gives every atom and molecule a subtle, constantly changing electrical personality, and these personalities, though they fluctuate randomly on ultra-fast timescales, somehow manage to coordinate with the personalities of nearby atoms and molecules to create attractive forces. It's as if the quantum world has found a way to create order and attraction from chaos and uncertainty. The strength of these quantum mechanical attractions depends on how easily the electron clouds around atoms can be distorted or polarized by external influences. Atoms with loosely held outer electrons, like the larger atoms found in the lower rows of the periodic table, create stronger London dispersion forces than atoms with tightly bound electrons. This is why larger molecules, which tend to have more loosely bound outer electrons, often stick to things more readily than smaller molecules. This quantum mechanical origin of stickiness helps explain some observations that might otherwise seem puzzling. For instance, why do the noble gases, helium, neon, argon, krypton, and xenon, which are chemically inert and don't form chemical bonds under normal conditions, still stick to surfaces under the right conditions? These elements have completely filled electron shells that make them very stable and unreactive, yet they can still be liquefied at low temperatures, and they do interact with surfaces in ways that can be measured and utilized. The answer is that even these chemically inert atoms have fluctuating electron clouds that can create London dispersion forces. The attractions are extremely weak, much weaker than the forces involved in chemical bonding or even in most other types of physical adhesion, but they're measurable and real. Even two helium atoms, which are about as unreactive as atoms can be, will attract each other through these quantum mechanical forces if they get close enough together. This universality of quantum mechanical adhesion means that everything sticks to everything else at least a little bit under the right conditions. The reason we don't notice this in everyday life is that these forces are usually overwhelmed by thermal motion, the random jiggling of atoms and molecules due to temperature. At room temperature, Atoms and molecules are moving around so vigorously that the weak attractions of London dispersion forces are like whispers in a thunderstorm, present but drowned out by the chaos of thermal motion. But at very low temperatures, when thermal motion slows down, or when other factors allow molecules to get very close together and stay there, these quantum mechanical forces can become significant and even dominant. This is part of why ultra-high vacuum technology is so challenging. In the nearly perfect emptiness of ultra-high vacuum chambers, individual gas molecules that do remain can stick to the chamber walls through quantum mechanical forces that would be negligible under normal atmospheric conditions. Creating and maintaining ultra-high vacuum requires understanding and overcoming these subtle quantum adhesion effects. Engineers have to choose materials for vacuum chamber walls that minimize these interactions, design pumping systems that can remove molecules even when they were weakly bound to surfaces, and develop techniques for cleaning surfaces so thoroughly that even individual molecules of contamination are removed. The quantum mechanical nature of molecular attractions also helps explain why adhesion is so sensitive to distance, more sensitive than our everyday experience might suggest. Quantum mechanical forces typically decrease very rapidly with distance, much more rapidly than classical forces like gravity or magnetism. Van der Waals forces, for example, decrease with the sixth power of distance, which means that doubling the distance between two molecules makes the attractive force 64 times weaker. This is why pressing surfaces together firmly is so important for achieving good adhesion. You're not just removing air gaps and bringing surfaces into contact, you're bringing molecules into the very narrow range where quantum mechanical attractions can operate effectively. At molecular scales, the difference between touching and almost touching can be the difference between strong adhesion and no adhesion at all. There's something almost magical about the idea that the stickiness we experience in everyday life ultimately traces back to the fundamental quantum mechanical nature of matter itself. The tape holding your notes to the wall, the water droplets clinging to your windshield after rain, the gecko walking across your ceiling. All of these depend on quantum mechanical effects that arise from the inherent uncertainty and fluctuation that exist at the deepest levels of reality. Modern technology is beginning to harness these quantum effects more directly and deliberately. Researchers are developing adhesive systems that take advantage of quantum mechanical tunneling effects, where electrons can essentially teleport through barriers that should be impenetrable according to classical physics. These quantum adhesives might allow new types of electronic connections that are stronger and more reliable than anything possible with classical adhesion mechanisms. There's also growing interest in quantum effects in biological adhesion systems. Some researchers suspect that the remarkable efficiency of certain biological adhesive systems might involve quantum mechanical enhancements that we're only beginning to understand. The gecko's foot, for instance, might be optimized not just for maximizing classical van der Waals interactions, but for taking advantage of quantum mechanical effects that enhance adhesion beyond what classical calculations would predict. As we develop quantum technologies like quantum computers, quantum sensors, and quantum communication systems, understanding quantum mechanical adhesion becomes increasingly important. These devices often rely on maintaining quantum states that are extremely sensitive to environmental disturbances, including the quantum mechanical forces between different components of the device. The study of quantum adhesion also connects to some of the deepest questions in physics about the nature of empty space itself. What we think of as empty vacuum actually contains quantum fluctuations, virtual particles that pop into existence and disappear so quickly that they can't be directly observed, but whose effects can be measured through phenomena like the Casimir effect. The Casimir effect demonstrates that even the vacuum between two surfaces can create adhesive forces under the right conditions. When two very smooth, very close parallel surfaces are placed in vacuum, the quantum fluctuations of empty space between them become restricted compared to the quantum fluctuations in the space around them. This creates a pressure difference that pushes the surfaces together with a measurable force. This is adhesion arising literally from nothing, from the quantum mechanical properties of empty space itself. It's a reminder that even our most fundamental concepts about matter and emptiness need to be reconsidered when we venture into the quantum realm. Empty space isn't really empty. It's a seething foam of quantum activity that can create real, measurable forces under the right conditions. Understanding these quantum mechanical underpinnings of adhesion doesn't just satisfy scientific curiosity. It opens up new possibilities for engineering materials and devices with properties that would be impossible to achieve without this deeper understanding. We're moving toward an era where we can design adhesive systems at the quantum level, engineering the very electronic structures of materials to create precisely the adhesive properties we need for specific applications. Some researchers are exploring whether quantum coherence effects, the quantum mechanical phenomenon that allows particles to exist in multiple states simultaneously, might be harnessed to create adhesives with entirely new properties. Imagine adhesives that could exist in superposition states, simultaneously sticky and non-sticky, until a measurement or interaction forces them to choose one state or the other. As we continue our gentle exploration of stickiness, let's turn our attention to the wonderful examples of adhesion that surround us in our everyday lives. Phenomena so commonplace that we barely notice them, yet each one a small miracle of molecular cooperation and quantum mechanical forces working in perfect harmony. These everyday examples remind us that we live in a world that is fundamentally held together by the same forces we've been exploring tonight. Consider, for a moment, the simple act of writing with a pen on paper. As you watch these words appear on your screen or imagine writing them yourself with a pen, millions of molecular interactions are occurring every second. The ink flowing from the pen onto the paper fibers involves countless van der Waals forces, hydrogen bonds, and sometimes chemical reactions. The ink doesn't just sit on top of the paper like a puddle of liquid on a waterproof surface. It actually penetrates into the microscopic structure of the paper, flowing into tiny channels between cellulose fibers and forming molecular-level connections that hold it in place. Different types of ink work through different adhesion mechanisms, each one optimized for specific purposes and conditions. Ballpoint pen ink typically uses dyes dissolved in oils that soak into paper fibers primarily through capillary action and form primarily physical connections through van der Waals forces. The oil-based carrier helps the ink penetrate into the paper structure, while the dyes themselves form attractions with the polar cellulose molecules that make up the paper. Fountain pen ink typically uses water-based dyes that can form hydrogen bonds with the polar molecules in paper, creating connections that are somewhat stronger than van der Waals forces but still reversible under the right conditions. This is why fountain pen ink can sometimes be removed with water or special solvents, while ballpoint pen ink is generally more permanent. Permanent markers use solvents that allow the ink to penetrate deeply into surfaces, and sometimes form chemical bonds that make the marks truly permanent. The solvents help carry the dye molecules into microscopic pores and crevices in the surface, where they can form multiple types of connections simultaneously. The fact that writing works at all is a testament to the selectivity and precision of molecular adhesion. The ink sticks strongly enough to the paper to remain legible for years or even centuries, but it doesn't stick so strongly to the pen mechanism that it can't flow out when we write. This delicate balance between adhesion and flow is carefully engineered through the chemistry of the ink formulation, the design of the pen mechanism, and the properties of the paper surface. Or consider something as mundane as dust accumulating on surfaces in your home. Each particle of dust, composed of everything from dead skin cells to fabric fibers to microscopic bits of rock and pollen, lands on surfaces and sticks there through the same van der Waals forces we've been discussing. The reason dust tends to accumulate rather than immediately falling off surfaces is that these surfaces provide countless opportunities for molecular-level adhesion. Interestingly, the amount of dust that accumulates on different surfaces varies dramatically based on their molecular properties and surface topography. Dust sticks more readily to surfaces that can form stronger intermolecular interactions with the diverse collection of molecules that make up household dust. This is why some materials seem to attract dust, while others remain relatively clean under the same conditions. Smooth, non-polar surfaces like glass or polished metal tend to accumulate less dust because they form weaker van der Waals interactions with most dust particles. Textured surfaces with lots of microscopic hills and valleys provide more opportunities for mechanical interlocking and larger contact areas for molecular adhesion. Surfaces with polar functional groups can form hydrogen bonds or electrostatic interactions with appropriate dust particles, leading to stronger adhesion. Static electricity adds another dimension to everyday adhesion that we've all experienced. When you pull socks out of the dryer and they cling to your shirt, you're experiencing adhesion created by electrostatic forces. These forces arise when different materials rub against each other and transfer electrons, creating regions of positive and negative charge that attract each other with forces that can be much stronger than van der Waals interactions. Electrostatic adhesion is typically more temporary than van der Waals adhesion, because the charges can be neutralized by moisture in the air, contact with grounded objects, or simply the gradual movement of charges through materials. But while it lasts, electrostatic adhesion can be quite strong enough to make your hair stand up, to make pieces of plastic cling to unexpected surfaces, or to cause that annoying shock when you touch a doorknob after walking across carpet. The kitchen provides a wonderful laboratory for observing different types of adhesion in action, often within the space of a single meal preparation. When you cook an egg, the proteins in the egg white undergo chemical changes that cause them to stick to the pan through a combination of chemical and physical adhesion. As the proteins heat up, they unfold and their internal chemical groups become exposed, allowing them to form new connections with each other and with the surface of the pan. Non-stick coatings work by providing a surface that forms only very weak van der Waals interactions with food molecules, making it easy to break the adhesive bonds that do form. The most common non-stick coating, polytetrafluoroethylene PTFE, has a molecular structure where fluorine atoms surround a carbon backbone. Fluorine atoms hold their electrons very tightly, creating a very nonpolar surface that has minimal attractive interactions with most other molecules. Honey demonstrates the complex relationship between adhesion and flow, showing how the same substance can behave as both a liquid and an adhesive depending on the timescale we consider. Honey is highly adhesive. It sticks to surfaces through hydrogen bonding and van der Waals forces, forming connections with polar surface groups on materials like wood, paper, or skin. But honey is also viscous, meaning it flows very slowly under the influence of gravity or other applied forces. This combination of high adhesion and high viscosity means that honey can stick to vertical surfaces without dripping, at least for a while. The balance between adhesive forces trying to hold the honey in place and gravitational forces trying to pull it downward creates those characteristic slow-flowing drips that eventually form when honey's weight overcomes its adhesive connection to a surface. The rate at which honey flows depends on temperature, with warmer honey flowing much more readily than cold honey. This happens because higher temperatures increase the thermal motion of molecules, making it easier for them to slide past each other and break the temporary connections that create viscosity. Even something as simple as salt or sugar dissolving in water involves adhesion principles working at the molecular level. The water molecules form such strong hydrogen bonds with the ions in salt, or the molecules in sugar, that these bonds overcome the forces holding the salt or sugar crystals together. The salt or sugar molecules become surrounded by water molecules that stick to them more strongly than they stick to each other. In your bathroom, you can observe adhesion in the way soap works to clean your skin and hair. Soap molecules are amphiphilic, meaning they have both polar and nonpolar regions within the same molecule. The polar heads stick to water through hydrogen bonding, while the nonpolar tails stick to oily dirt and skin oils through van der Waals forces. This allows soap to create connections between water and substances that normally wouldn't mix, enabling the water to wash away dirt and oils that it couldn't remove on its own. The mirror in your bathroom might fog up after a hot shower, demonstrating how water vapor condenses on cool surfaces through the same molecular adhesion forces that allow liquid water to stick to glass. The tiny water droplets that first form grow larger as more water molecules stick to them, eventually creating the continuous film of water that fogs the mirror. The condensation process is driven by the lower energy state of liquid water compared to water vapor at the same temperature. When water vapor molecules encounter a cool surface, they can release energy by forming liquid droplets, and the energy released helps stabilize the adhesive connections between the water and the surface. Even the way fabrics hold together involves adhesion at multiple levels. The individual fibers in a fabric stick to each other through van der Waals forces and sometimes hydrogen bonding, depending on the chemical nature of the fiber material. In woven fabrics, the mechanical interlocking of the weave provides additional cohesion, creating a network of physical connections that supplement the molecular adhesion between individual fibers. Some modern fabrics include adhesive treatments that help fibers stick together more strongly, improving the fabric's durability, appearance, and performance. These treatments might involve applying polymer coatings that enhance interfiber adhesion, or chemical modifications that increase the number of hydrogen bonding sites along the fiber surfaces. When you put on moisturizer or sunscreen, You're applying substances specifically designed to stick to your skin through molecular adhesion, while also providing their protective or conditioning benefits. These products need to adhere well enough to stay in place and provide lasting protection, but not so strongly that they can't be removed when desired or that they interfere with normal skin functions. Skincare formulations often include ingredients that enhance adhesion to skin proteins while maintaining the flexibility and breathability that healthy skin requires. The formulation chemists who develop these products must balance adhesion, protection, aesthetics, and safety in complex ways that require deep understanding of both skin chemistry and adhesive principles. Your smartphone or tablet screen demonstrates sophisticated adhesion technology in multiple ways. The touchscreen responds to your finger because of the electrical properties of your skin and the capacitive sensors embedded in the screen, but this interaction also involves adhesive forces. The slight dampness of your skin can form temporary adhesive connections with the screen surface that enhance the sensitivity and accuracy of touch detection. The screen protector that might cover your device stays in place through carefully engineered van der Waals adhesion that's strong enough to hold the protector in place through normal use but gentle enough to allow removal without leaving residue or damaging the underlying screen. The adhesive layer on screen protectors is often designed with microstructured surfaces that maximize contact area while minimizing the formation of permanent bonds. Even breathing involves adhesion principles in ways you might not expect. The moisture in your breath condenses on cold surfaces through the same mechanisms that create dew on grass in the morning. The water molecules in your breath stick to cool surfaces when they lose enough thermal energy to form stable connections with the surface molecules. In your lungs, the exchange of oxygen and carbon dioxide depends on adhesive interactions between gas molecules and the wet surfaces of alveolar membranes. The thin film of water that lines your lungs provides a medium for gas molecules to dissolve and stick temporarily before being transported by your bloodstream to cells throughout your body. These everyday examples remind us that adhesion isn't just a curious scientific phenomenon that operates in laboratory experiments or exotic applications. It's fundamental to almost everything we interact with in our daily lives, from the moment we wake up and our feet stick to the floor through friction, to the way our toothpaste sticks to our teeth to clean them, to the way our clothes cling to our bodies and protect us from the environment. Understanding these everyday adhesion phenomena can even help us solve common problems and make better choices in our daily lives. Knowing that adhesion depends on surface cleanliness and molecular compatibility can help us choose the right cleaning products for different situations. Understanding that static electricity is a form of adhesion can help us reduce static cling in our clothes through the use of fabric softeners or anti-static treatments. Recognizing that different materials have different adhesive properties can help us select the right tape, glue, or fastener for household repair tasks. There's something wonderful about realizing that the same fundamental forces that allow geckos to walk on ceilings are also responsible for keeping the words in this script visible on your screen, for holding dust to the surfaces around us, and for enabling the countless other adhesive interactions that make our everyday lives possible. It connects us to the deep physics that governs our universe, while also helping us appreciate the molecular marvels that surround us every moment of every day. This perspective can transform how we see the ordinary world around us. Instead of taking adhesion for granted, we can marvel at the sophisticated molecular engineering that makes simple things like writing, cooking, cleaning, and getting dressed possible. We can appreciate that our entire technological civilization depends on our growing understanding of how to control and optimize the forces that make things stick together. As we near the end of our gentle exploration, let's take a moment to reflect on the deeper philosophical implications of what we've discovered about stickiness and the forces that hold our world together. There's something profoundly beautiful about the idea that the universe, at its most fundamental level, is constructed through attraction and connection, rather than through separation and isolation. Think about what this means for our understanding of reality itself. At the smallest scales we can imagine, smaller than atoms, smaller than subatomic particles, there are no truly isolated objects. Every piece of matter, every quantum of energy, every fluctuation in the fabric of space-time exists in a web of subtle attractions and influences that extend outward like invisible threads, connecting all things to all other things. The forces that make things stick together reveal that everything in our universe is, in a very real sense, connected to everything else. The quantum mechanical fluctuations that create van der Waals forces between molecules on your skin are related to the quantum fluctuations that existed in the early universe and eventually led to the formation of galaxies, stars, and planets. The molecular adhesion that allows water to climb through plant stems is connected to the gravitational forces that allow planets to hold onto their atmospheres and create the conditions where life can exist. This interconnectedness operates at scales ranging from the quantum mechanical, where electron clouds fluctuate in response to distant influences, to the molecular, where van der Waals forces create bridges between separate substances, to the biological, where adhesion enables life itself, to the cosmic, where gravitational attraction holds together the large-scale structure of the universe. It's as if the universe has a fundamental preference for connection over isolation, for cooperation over independence, for harmony over chaos. This preference emerges not from conscious intention, but from the mathematical structure of physical laws that govern how energy and matter behave under all possible conditions. When we understand that adhesion emerges from countless individual molecular interactions, each one tiny but collectively creating remarkable effects, we see a principle that extends far beyond physics and chemistry. Complex phenomena often arise not from single powerful forces, but from the cooperation of many smaller influences working together in coordinated ways. This pattern appears in biological systems where countless individual cellular interactions create the sophisticated behaviors we observe in living organisms. It appears in ecosystems where countless individual relationships between organisms create stable, resilient communities that can persist for thousands of years. It appears in human societies where individual actions and connections create cultures and civilizations that transcend the capabilities of any individual person. It even appears in consciousness itself, where the cooperation of billions of neurons creates the rich inner experience of awareness, thought, and emotion. Just as molecular adhesion emerges from quantum mechanical interactions that are individually too small to notice, consciousness might emerge from neural interactions that are individually too simple to constitute awareness. The sensitivity of adhesion to distance and surface conditions reminds us how important proximity and preparation are for creating strong connections in any domain. Just as molecules need to be brought close together and surfaces need to be properly prepared for adhesion to occur, ideas need to come into close contact with prepared minds for understanding to develop, and people need to approach each other with openness and vulnerability for deep relationships to form. This suggests that creating strong connections, whether molecular, intellectual, or social, often requires patience, careful preparation, and the willingness to bring different elements into intimate contact despite the barriers that might normally keep them separate. The reversible nature of many adhesive interactions offers another profound insight into the nature of successful systems. The strongest and most resilient systems are often those that can both connect and disconnect, as circumstances require, that can form bonds when beneficial and release them when change is necessary. Biological systems excel at this kind of dynamic equilibrium. Cells can stick together to form tissues when cooperation is beneficial, but they can also separate and migrate when growth, healing, or adaptation requires it. Ecosystems maintain stability through countless connections between species, but they can also reorganize and adapt when environmental conditions change. Human societies and relationships show similar patterns. The healthiest communities and partnerships are often those that provide strong support and connection, while also allowing for individual growth and change. Too much rigidity leads to brittleness and eventual failure, while too little connection leads to fragmentation and loss of collective capability. The history of human adhesive technology mirrors our growing understanding of cooperation and connection more broadly. Early adhesives were discovered rather than designed, just as early human societies developed through trial and error rather than systematic planning. But as our understanding deepened, we became able to engineer both materials and social systems more intentionally, creating bonds with precisely the properties we needed for specific purposes. The quantum mechanical foundations of adhesion remind us that uncertainty and fluctuation, rather than being problems to be eliminated, are actually sources of creative possibility. The random fluctuations in electron clouds that create London dispersion forces suggest that randomness and order can work together to create stable, functional systems. This has implications for how we think about everything from economic systems to artificial intelligence to personal creativity. Instead of trying to eliminate uncertainty and control every variable, we might do better to create systems that can harness uncertainty and turn fluctuation into opportunity, much like the quantum mechanical systems that turn random electron fluctuations into stable attractive forces. Perhaps most remarkably, the study of adhesion reveals that the universe is fundamentally constructed through gentle forces rather than violent ones. The strongest bonds often result not from powerful individual connections, but from countless gentle attractions working in harmony. There's something deeply hopeful about this realization. It suggests that cooperation and gentleness might be more fundamental to reality than competition and force. When we observe a gecko walking on a ceiling, we're witnessing the macroscopic expression of quantum mechanical principles operating through billions of molecular interactions. It's a reminder that the grand and the tiny are intimately connected, that the patterns we see at one scale often reflect the principles operating at all scales. The selectivity of molecular adhesion, the way different molecules stick preferentially to certain partners while avoiding others, mirrors the selective nature of all meaningful connections. Just as adhesion works best when there's compatibility between the surfaces being joined, human connections flourish when there's compatibility between individuals, while still allowing each to maintain their unique identity. The time dependence of many adhesive interactions reminds us that the strongest bonds often develop gradually. Just as tape becomes harder to remove the longer it's in contact with a surface, human relationships often deepen with time as people adjust to each other and find increasingly stable configurations of mutual support and understanding. Even the failures of adhesion teach us important lessons. Adhesive failure often occurs not because the bonds themselves are weak, but because the preparation was inadequate or because the surfaces weren't compatible. This suggests that in any system where we want to create strong connections, whether molecular, social, or intellectual, the preparation and compatibility assessment are just as important as the strength of the binding mechanism itself. The environmental sensitivity of adhesive systems reminds us that all connections exist within larger contexts that affect their stability and strength. Temperature, humidity, chemical exposure, and mechanical stress all influence how well things stick together. Similarly, human relationships and social systems are influenced by their environments in ways that can either strengthen or weaken the bonds that hold them together. Understanding these environmental influences can help us create conditions that support the connections we value, while recognizing that even the strongest bonds may need occasional maintenance and care to remain healthy over time. As we've explored the world of stickiness together tonight, we've discovered that adhesion is far more than just a practical phenomenon useful for tapes and glues. It's a window into the fundamental nature of matter, energy, and connection itself. The same forces that hold atoms together in molecules, molecules together in materials, and materials together in structures also operate in countless other systems throughout our universe. Understanding adhesion helps us appreciate that our world is held together not by rigid constraints imposed from outside, but by countless flexible, responsive connections that can adapt to changing conditions while maintaining overall stability. It's a model of resilience that might inspire how we approach challenges in our own lives and communities. There's something deeply satisfying about understanding that the ordinary miracle of tape sticking to paper involves the same quantum mechanical principles that govern the behavior of distant galaxies and the fundamental particles that make up all matter. It connects us to the deep physics of our universe, while also helping us appreciate the sophisticated molecular engineering that makes our daily lives possible. This understanding also suggests a profound unity underlying the apparent diversity of natural phenomena. The forces that allow water to climb through plants, that enable geckos to walk on ceilings, that hold our cells together into living tissues, and that bind the pages of a book together are all variations on the same fundamental theme, the universal tendency of matter to reach out across space and form connections. As we conclude our gentle journey through the sticky universe, I find myself returning to that question I asked at the beginning. Where are you watching from tonight, and what time is it where you are? Now that we've explored together the invisible forces that hold our world together, perhaps you have a new appreciation for the countless molecular connections that surround you at this very moment. The air you're breathing right now contains molecules that stick to each other through van der Waals forces, allowing gases to behave as continuous fluids rather than collections of isolated particles bouncing around independently. The chair or bed you're sitting or lying on holds together through adhesive forces operating at scales from the molecular to the macroscopic, creating a stable structure that can support your weight while remaining comfortable. The screen you're watching displays images through the precise control of electromagnetic forces that are cousins to the electrostatic attractions we've discussed tonight. Even the light that carries these words to your eyes involves interactions between photons and the molecules in your retinas that are fundamentally adhesive. In nature, the photons stick temporarily to visual pigments, triggering chemical changes that become the signals your brain interprets as vision. Your own body is a magnificent demonstration of adhesion principles operating at every level of organization. Your cells stick together through protein structures that involve both chemical bonds and physical interactions. Your bones are composite materials, where mineral crystals are held in a matrix of organic molecules through sophisticated adhesive architectures that provide both strength and flexibility. Your muscles and tendons demonstrate how biological materials can be both strong and flexible through evolutionary optimization of adhesive connections at multiple scales. The thoughts you're thinking right now depend on neurons forming temporary connections through chemical adhesion at synapses, allowing information to flow through your brain in patterns that create consciousness and understanding. In a very real sense, your ability to contemplate the nature of stickiness is itself made possible by biological adhesion operating in your nervous system. As you prepare for sleep tonight, you might find yourself noticing adhesive phenomena you hadn't paid attention to before. The way your sheets cling to your skin through weak van der Waals forces and static electricity. The way moisture from your breath might condense on a cool window through the same hydrogen bonding that makes water such a remarkable substance. The way dust motes dance in moonbeams, each particle eventually finding a surface to stick to through the gentle but persistent molecular attractions we've explored together. There's something wonderfully peaceful about falling asleep with an understanding of the forces that hold our world together. Instead of feeling surrounded by separate, isolated objects in an indifferent universe, you can rest in the knowledge that you exist within a cosmos that is fundamentally interconnected, where everything influences everything else through gentle but persistent attractions that operate across all scales from the quantum to the cosmic. The same quantum fluctuations that create van der Waals forces between molecules are related to the quantum fluctuations that seeded the formation of the first stars in the early universe. The molecular adhesion that allows water to nurture life on Earth is connected to the gravitational forces that keep our planet in the habitable zone around our sun. The gecko's ability to walk on your ceiling emerges from the same fundamental principles that allow matter and energy to organize themselves into the complex, beautiful structures we see throughout the natural world. As you drift off to sleep, perhaps you can carry with you a sense of wonder at the elegant simplicity underlying the apparent complexity of our sticky world. Whether it's the tape holding a note to your refrigerator, the water droplets clinging to your window after rain, or the countless cellular connections that make your body function, all of these phenomena emerge from variations on the same beautiful theme, the universal tendency of matter to reach out across empty space and form connections with other matter. This tendency toward connection and cooperation, manifested in everything from quantum mechanical attractions to ecological relationships to human social bonds, suggests something hopeful about the fundamental nature of reality. We live in a universe that seems biased toward connection rather than isolation, toward harmony rather than chaos, toward the emergence of beauty and complexity from simple underlying principles. Sweet dreams, fellow travelers in this sticky universe. May your rest be as peaceful as molecules settling into their lowest energy configurations. May your sleep be as gentle as hydrogen bonds forming between water molecules, and may you wake tomorrow with a renewed appreciation for the invisible forces that make our world not just possible, but wonderfully, beautifully, mysteriously interconnected. The gentle forces that hold our world together will continue their patient work while you sleep, maintaining the countless connections that make life and consciousness and dreams possible. And perhaps in your dreams tonight, you'll find yourself walking like a gecko on the ceiling of possibility, held aloft by nothing more than the quantum mechanical gentleness that underlies all of reality, moving with confidence through a universe that is fundamentally designed for connection, cooperation, and the endless exploration of what's possible when separate things choose to stick together. Good night, and thank you for joining me on this exploration of the secret forces between surfaces. Until we meet again in the space between wakefulness and sleep, may you rest well in the embrace of a universe that is held together by nothing more and nothing less than love expressed at the molecular level, the universal attraction that draws all things toward all other things, creating the beautiful, interconnected, sticky world we call home.